Talk about uncertainty now. And the uncertainty discussions and the error budget discussions kind of mixed, but I'm going to concentrate on just talking about some of the uncertainties. We may not need to spend much time on this because a lot of the questions have already addressed some of these, so I'll try to, if I think we've covered it, I'll just say we covered it. If you want to talk more about it, then stop me and ask questions as you've been doing already. The issues in terms of uncertainty for the reflectance retrieval is sampling. So the idea is that we're trying to get the reflectance in the ground that's representative of what the satellite sensor is seeing. And there's things that go in terms of the angular field of view, the spatial differences. How do I know that my 80 meters by 300 meters is exactly the same region that's seen by the satellite sensor? And it can at least be off by half a pixel, at the very least. So there's some spatial systems that we have to worry about. The spectral sampling also. And what's nice is we're oversampling spectrally, and then we're combining those data into 10 or 20 nanometer spectral bands, so that becomes less of a problem. The instrument, the ASD is a source of issue. Field of view is too large, the field of view is too small. See, like how that happens? So I can have problems because I'm too large a field of view, and I have problems because I'm too small a field of view. The instrument itself can change with time. The advantage of doing ratios is that we minimize those effects. But if we take too long between the reference measurements, then they can creep in. Assumption of the bidirectional nature of the problem. We'll talk a little bit about that. The temporal changes in solar zenith, the panel, the atmosphere, the reference leveling. These are all things that can go wrong as you try and do these collections. So the reference with time. And this is really only a problem if you're assuming that the reference is constant. The work that we were doing is we would keep track of when we were at the panel, and we would incorporate the change in the panel BRF as we were collecting data. So this little small shift in terms of basically doing a measurement early in the day and a measurement later in the day of the panel reflectance changing by about 0.25%, 0.5%, just in that 30-minute time period. But we would account for this, so that there's still an uncertainty, but instead of being 0.25% to 0.5%, it's really more like 0.03 to 0.05%. Instrumental effects. This was one where we purposely knew what the ASD was doing, and we collected a data set that we knew would show this because I was trying to get some notes for class. And the temperature dependency of the silicon detector causing issues in the blue. And then out here, the silicon detector has a thermal problem that as the detector is warming up and cooling off, its responsivity is changing. And then you have now a problem in terms of temporally it's not what you think it should be. And what's odd is most people go, well, this was the sad thing is originally everybody went, well, this must be the shortwave infrared because the indium gallium arsenide detectors are not that good. It must be the indium gallium arsenide that's causing problems. Because the responsivity of these detectors is low at this wavelength. But in reality, it's silicon, and what ASD did was develop an interpolation scheme that allowed you to basically fill in this gap. What they really recommended was that you let it warm up for about 45 minutes to 3 hours. So now you're out at your test site, and assuming you got to your site 3 hours beforehand, you can let it run, but if it was hot, then you might end up causing it to fail because you got it overheated. And I'll point this out, it's not that this is a bad instrument, it's not that this is, you can claim this is a design flaw, but we're using it in a way that it was not originally intended, and they have a methodology that says if you operate it this way, you will not see these problems. And then the question becomes, are you able to operate it in a way that you can avoid the problem? Field of view. The field of view of the spectrometer is actually closer to about this size. But to make it clearer, let's assume the field of view is this large. I'm seeing parts of playa, and that can become an issue. What's also interesting is we have what's called out-of-field response. So even if you have a very small 8-degree field of view, you still may get light coming in from far outside. You'll notice that the lid is below the panel. In the old days, the students would just drop the lid somewhere. We had to tell them, no, make sure the lid goes under the panel. They'll come. Because at least if we have an out-of-field contribution from this surface in the measurements, that'll be the same out-of-field contribution when I'm standing over here on the site. So it will mitigate to a large extent. It's not perfect, but it's not going to cause a very large uncertainty. It just causes some uncertainty. It really becomes, if the area around your panel is much different in reflectance than the area you're out measuring, then you'll have a size of source problem. So it is something to be concerned about, but it's more the smaller field of view being on the panel, making sure that you're not being affected by spatial heterogeneity of the panel. Some of the others is one of the experiments we did, and I just have this is because we took basically an airborne system outside because it's a really well calibrated, stable system, and so we wanted to get a radiance measurement that would fly at ground level. And then we were going to fly it in the aircraft and see how it matched up with some of our measurements. And it had this little tiny field of view, but it had this really massive size. So it was really an interesting problem of trying to figure out where do we put the panel, what height do you put the panel, what impact you're going to get because of shadows and all the structures back over here, and what do you do to try and minimize those kind of things. It's a picture that brings to your mind that just standing at a panel will have an impact on the measurements itself. Going back to Chris's questions about diffuse light. So what we did was develop or examine the impact of it. And the way you do that is when you take your panel measurements, you basically go ahead and you also take a shaded panel measurement. This gives you the downwelling diffuse light component. In order to process it properly, though, because what you want to do is compare bidirectional reflectance to the hemispheric directional. You then have the shadow of the ground that you're measuring. And so if you wanted to actually make this correction in reality, what you would have to do is every single measurement you had at your test site would have to be shaded and unshaded as well as for the panel. So our goal in this case was to prove that we really had no impact because of the diffuse light for typical sky conditions. And some of the days that we did this on, they were not even typical. We still could not, this day we did not see a significant difference in the retrieved reflectance except at the very shortest wavelengths. And even then, the correction that we put in place created a larger uncertainty than if we did nothing at all. So we got more variability in our output by doing a correction for diffuse light than we did by just ignoring it. And so we know that we have at wavelengths shorter than 450 nanometers, we have a slight bias that might creep in because of the fact that we're not truly bidirectional. So this effect, just to reiterate, we're assuming we're measuring bidirectional reflectance. Sunlight only, and coming up from a directionality off the ground. Well, the directionality from the ground, that's defined by the radiometer. We have that covered. We know we don't have just sunlight because we can see the sky. So you have a hemispheric component that's stronger at the short wavelengths than it is at the longer wavelengths. And this experiment showed that for us, at our test sites, it was not a dominant error source. Now, as we start to go from 2.5% to sub 1%, this will have to be taken into account, which will then force us to have a different sampling methodology. ASD malfunctions. One of the reasons that we included the gray panel was to try and characterize what are called type B uncertainties, statistical uncertainties in the instrumentation, random fluctuations, variability. I probably have it wrong. I'll catch myself later today, I'm sure. And the idea is that you stop and you stare at this gray panel and you're standing and just measuring it, and the variability of that gives you an idea of how much your instrument variability is. And it gives you an idea of that. So that was the reason we implemented it. And then all of a sudden, with one of the instruments, we started seeing some odd behavior on the test site. We did some comparisons looking at the ground. So this is the ratio of the site between two instruments. And here it is over the gray panel. And that just bothered me. And then we stopped and we went, okay, you know what the difference is. When we're on the site, we're walking. When we're at the panel, we're standing still. Fiber not moving, fiber moving. Broken fiber moving. In the ASDs, the way the fibers go is the fiber bundle splits out. And each little fiber piece goes to a specific portion of the detector, and each portion of the detector in the visible near infrared is a different wavelength. So it also is the problem that if you have an ASD, they should be telling you that you either need to rotate your field of view or you need to move it slightly. Because if you just stop and stare, each individual wavelength sees a different location on the ground because it's a different fiber. It's just one of these odd little features, and the fact that we didn't catch it, again, if we were doing radiances, this would have shown up almost immediately in our data set. And when we saw the left-hand graph was, well, how did the panel did? The gray panel data looked fine. We couldn't see any problem. We did not see a problem. And that was simply because we weren't moving. So the further use of the gray panel, it just allows us, we can measure it in the laboratory, which is a nice way to do things, and then see how things look out in the field. And the idea is that if we're seeing an odd behavior of the ASD over the site, we can go back and look at the gray panel, because if you go back and look at your reference, you're assuming you know what the reference is. But the gray panel, we can retrieve its reflectance both in the lab and in the field using that same reference as we're doing our site measurements, and they're about the same reflectance level. And so what you basically can do is look at the gray panel is, the spectral line is our kind of our green line there. The test site is the change in the test site with time, and then the gray panel. And it just tells us that, in this case, everything is sort of operating nominally. You know, we're seeing slight little fluctuations of about a percent or so, and that we can blame in terms of how the panel itself is changing with time. And so we have that accounted for. And then that purple has to be something that's related to how we're sampling the site. There has to be something related to how the instrument's behaving with time. And the fact that we've got this big jump in the shortwave infrared tells us that we didn't warm it up properly. And we can do more of those comparisons. That's more than we need. But you can also, and this is the part that started to show that we had some issues that we had to figure out, is here's what the laboratory calibration for the gray panel is, and here's the retrieved reflectance. And that's larger than what you should expect. And what we figure is we had a out-of-field response that we had to correct in that case. We're getting a little bit of the black edge of the panel because it's a small panel. And what it told us that in order to do this properly, we really need to have a larger panel.